So, other addressing that we have is the absolute jump type of instruction. So, in the absolute jump instruction, so the jump address is specified explicitly. The problem with relative addressing is that this jump address has to be within 256 bytes from the current location. So, that may not be always possible. Okay. So, what we can do is that we can take a small relative jump, and from there we may have to take a long jump. So, that is by means of absolute addressing. So, you cannot always deny the use of absolute addressing. So, in case of absolute jump instruction in 8051, so we have got different version. One version is the AJMP instruction. So, this AJMP is an absolute jump, but here this it is limited to 2 kilobyte from the that is the current memory block. So, limited in 2 kilobyte. So, you cannot go beyond 2 kilobyte. So, this why? Because this address that is mentioned is this A0 to A7 and this A8 to A10. So, total 11 bits are devoted for keeping the offset, and by 11 bits. So, you can mention the numbers in the range of total range of numbers that you can have is 2 kilobyte. So, as a result, so it cannot be more than 2 kilobyte. So, we can have this this AJMP next instruction. So, this next value is 07 this next value is here. So, that is this instruction ends at 0705. So, next instruction this one is at address 0706, this is at 0706. So, this 0706, so this is it will be so U1 is the code that we have, okay, is for AJMP. So, actually these bits are actually mixed. So, you cannot really differentiate very easily. So, you have to distribute it and then only it will come. So, this is not 07. So, this will be based on if you just look into the code, then it will be like this. So, here this 0706 is put directly, it is distributed in these bits and these bits. Okay. So, this is actually this is the other version of this jump instruction, which is LJMP. So, this is LJMP instruction. So, this is LJMP, there is a long jump. So, here we do not have the restriction. So, in the SJMP instruction we had this in the SJMP instruction we had this thing, this offset is only 11 bits A0 to A10, but in this LJMP instruction, so offset is total 16 bits. So, you can branch across the total 64K address space that you have. So, the range is very high, all 0000 to FFFFX. So, here when we are saying like LJMP next, so LJMP next, so it is so the value will be calculated. So, next address is 0707 and the opcode is 02 and then the whatever be the address, so that will be coming here. So, that way this long address will be calculated. So, we have got these three variants of jump instruction. We have got the relative jump specified with the relative jump instruction specified as SJMP. We have got this absolute jump instruction specified by AJMP, and this absolute jump instruction is a 2 byte instruction and a relative jump instruction is also a 2 byte instruction, but this LJMP instruction is a 3 byte instruction. So, that way this LJMP is slightly costly in terms of the area requirement, and when this microcontroller is being used, you know that this memory space is scarce. So, we will like to save as much memory as possible in the code part. So, if it is not absolutely necessary, we should not use LJMP. So, we should restrict us to AJMP instruction, because that will require 1 byte less, otherwise there is no difference. The next important concept that we have is the stack. Okay. So, the stack as we have seen that is so it is a part of memory, and the stack pointer, it points to the top of the stack. So, we can have two operations, push and pop, but the push operation will push the next whatever the value that we want to put into the stack, into the location pointed to by stack pointer, and the pop will take out the value from the top of the stack and get into the location that we want. So, for stack oriented data transfer, so only one operand can be specified. So, we have to just tell the value that we are trying to push or pop, and the stack pointer is the other operand. So, because the memory access will be in terms of the stack pointer only. So, in the only direct addressing it can be used. So, we can for before doing any stack operation, the most important thing is to initialize the stack pointer. So, if we do not initialize the stack pointer properly, then this stack pointer may be pointing to some garbage location, and then this push pop will arbitrarily modify some memory location. So, what is done? So, for before doing any push pop operation, the program should first set this stack pointer, and that may be done at the beginning of the program, and later on when it is so as it is doing other the push pop operation. So, since the program has set it properly, it is expected that it will not corrupt any of the important program and data parts. So, here move sp comma hash 0x40 hex. So, the value of 40 hex will be put into the stack pointer. So, stack pointer is initialized to that, then push 0x55. So, what happens is that the memory first this stack pointer is updated, stack pointer is updated by 1, incremented by 1, then the memory location stack pointer gets the value 55x. So, what happens actually is since stack pointer is at 40, so memory location 41 will get the content of memory location 55. So, this is again you see that one way of transferring data between two memory locations. Okay. So, from memory location 55 we are transferring the data to the memory location 41. The other instruction that we have is the pop instruction. So, you can again mention some address, or you can mention the special registers. So, pop B, so B gets the value of memory location 55. So, you see that can only the we can only specify RAM or SFR registers to push or pop. So, we can for to push pop accumulator, so we should use ACC and not A. So, A cannot be used because A is treated as a register, but ACC is treated as a special function register. So, that is why we cannot use A, but we have to use ACC in the instruction. But anyway, apart from that, so you can directly specify the memory addresses for those registers. So, push A is invalid, push R0 is invalid, push R1 is invalid. So, these three are invalid because these are not, so I cannot mention registers like this. We can write like push accumulator, push ACC, push PSW, push B, push 13 hex, push 0. So, all these can be done. Okay. Or you can even write in terms of the special the register numbers like push 0E0 hex. So, that is same as this push ACC, then pop 0F0 hex. So, that is same as this pop B. Okay. So, that way so this push pop instruction. So, these assemblers, so they will not accept these things, but they will accept this one. So, that is just for you can say some sort of convenience. Okay. So, there is another type of data transfer instruction which is known as the exchange. Okay. So, exchange, so this exchanges the values of 2 bytes. So, XCH A comma 30 hex. So, the content of memory location A will be exchanged with memory location content of register A will be exchanged with memory location 30. And again the same thing, that all this instruction, this A part is fixed. So, XCH A, so this part is fixed. So, only the second thing can be specified. So, you can say like XCH A comma at the rate R0. So, A will be exchanged with memory location R0 pointed to by R0, and there is a special version XCH D. So, it is the exchange digit. So, only 4 bits are exchanged. So, this lower order 4 bits will be exchanged like between A and R0, this lower order 4 bits will get exchanged. Okay. So, this is useful in many cases, like particularly for operating system design. So, this type of exchange instructions are useful, particularly when we are going to implement say semaphore type of synchronization primitives, then this type of exchange of data will be useful. Next we will look into bit oriented data transfer. So, this is a very powerful feature that this 8051 microcontroller has, and for that matter most of the microcontrollers will see that it has got this bit addressability, and this makes it powerful because many times we have to set the different bits in a different fashion. So, making the mask pattern accordingly and setting the bits that way, so it requires a large amount of code, and maybe we just set the number, then do a left shift or right shift to come to the proper pattern and all that. So, those can be avoided, and we can just access individual bits directly to put the values there. So, this bit oriented data transfer, so it transfers between individual bits. So, this carry flag, a carry that is C, that is used as single bit can be used as a single bit accumulator, and this RAM bits 20 to 2F. So, they are all bit addressable. Like we can have move C comma P 0.0. So, this port 0's bit number 0 will come to the carry flag. Then this 67 hex, like say this one. So, this can be moved to the carry flag. So, we can have it like this. Then this 2C hex dot 7. So, 2C hex is this one dot 7. So, this is the same as that bit 67. Okay. 67 hex, so that is same as that one. So, it will be so bit number 67 hex and this 2C hex dot 7. So, they are same. So, they will come to the carry flag. So, this way we can use these bit oriented instructions for data transfer. Now, the special function registers that are bit addressable. So, you see that if you look into the pattern, like say this P0, then this Tcon, so they are bit addressable, others are not. So, you see that the addresses which end with 0 or 8 are bit addressable, like 8088, 9098, they are bit addressable, and all 4 parallel IO ports, so they are all bit addressable. So, that is there. So, P0, P1, P2, P3, they are bit addressable, okay. And this the registers who end with 8, okay, or 0, that is divisible by 8. So, they are all bit addressable. Next, we will look into data processing instructions. There are several data processing instructions in 8051, like add, subtract, increment, decrement, multiply, divide, decimal adjust. So, like that. So, we can have like arithmetic instruction like add a comma byte, add a to byte and put the result in a register, add c comma byte. So, add c a comma byte. So, it will add with carry. So, it is a plus byte plus carry will be put into the a register. Then subtract with borrow SUBB. So, that will be there. So, this way we can have a number of such instructions. So, we will see some of them like add a comma byte, a gets a plus byte, and add c a comma byte, a gets a plus byte plus c. These instructions will affect 3 bits of PSW, like it will affect this carry bit, CY, auxiliary carry bit, and the overflow bit. So, if C equal to 1, if the result of add is greater than FF, so the carry is generated, then the carry flag will be set. The auxiliary carry will be 1 if there is a carry from bit 3 to bit 4. Okay. So, if there is a carry, then after the nibble, if there is a carry, then this bit will be set to 1, and this overflow will be set if there is an overflow carry coming out of bit 7, but not from bit 6. So, there is a carry out of bit 7, but not from bit 6, or vice versa, then the overflow flag will be set. So, these are the instructions that will affect the PSW register, like the add affects C carry, overflow and auxiliary carry, add C again affects all of them. Now, some of the interesting things that we have got is multiply instruction that will set the carry to 0 and the overflow is affected, but not the other one. Similarly, division, so this will set the carry flag to 0 and it will not affect it will affect the overflow, but not the accumulator. Then set B carry, so as the name suggests, the carry should be set to 1, set bit carry. Okay, so, this carry is set to 1. Similarly, clear carry will make the carry bit 0. Complement carry, so whatever be the current value of the carry bit, so that will be complemented. Then we have got AND logical C bit. So, this will be ANDing the bit with the carry. So, that may be if this bit is 0, so it is clear carry. So, if this bit is 1, so this will be some the previous will continue. So, you can you can mention some bit number with which the carry will be ANDed. Then we have got this move C. Okay, so, we will see these instructions. Now, like this addition example, like move a comma 3f hex and then add a comma hash d3. So, what will be the value of this? So, if we do this addition, so it will be like this. Now, so the things that are affected is carry equal to 1, AC equal to 1 and OV equal to 0. Then if we 2's complement notation, so we have got this number, it is 7f and this is 80. So, 80 is minus 128 and this number is 7f is 127. If you do the addition, then the result should be minus 1. So, in the binary notation, if you do the addition, so 1 1 or so this the hexadecimal equivalent is ff, which is minus 1. So, similarly, if this is 127, so this is number 127, this is 115. So, if you add it, then there will be an overflow, because this value 242 cannot be represented in 8-bit 2's complement format. So, there is an overflow, and similarly, we have got say negative of 113. So, this is coded like this, negative of 45 coded like this, again there will be an overflow, because we cannot represent the number there. Okay. But if we do it, say this is positive and this is negative. So, after doing the addition, there is no overflow. So, that way we can have different addition results affecting the carry, auxiliary carry, overflow flags. Now, suppose we are writing a program that will be doing this z equal to x plus y. So, it will add the contents of locations 78 hex and 79 hex and put them in the register into the memory location 7a. So, what we do? So, we define 3 constants x, y and z, and as I said that this EQU or equal. So, this is a assembler directive that tells the assembler that in my program wherever I am writing x, you should replace it with 78. So, that is a constant number, and org 00 hex. So, this means that so this is the assembly will start at location 00 hex. So, the program when it is loaded, so the first instruction LJMP main will be at location 00 hex. Okay, so, if you look into the memory map, so it will be like this at location 0000. So, it will put the instruction LJMP main. Now, for main, so this is before that we have got this org 100. Okay. So, this at location from 0100 my actual program starts. Okay. So, there I have got this move x and all these codes, they are starting from this point onwards. So, when we start the program, start the system, so it should go to location 0100. So, the assembler when generating the object code, so it will do it like this, that at location 0000 it will put the instruction LJMP 1000, and at location 0100 onwards, so it will be putting the code for this piece of program. So, when the program will actually be executed, the PC, when we reset the processor, the PC will be 0000. So, it will come to this instruction and it will make this execute the LJMP 0100. As a result, it will start executing from this point onwards. So, what are we doing here? So, first we are moving the content of x, move a comma 78 hex. So, content of memory location 78 will come to a, then add a comma y. So, content of memory location 79 will be added to a, and then move z comma a. So, content of the accumulator will be saved into the memory location 7a hex. So, this way this program will be executed and do the addition. So, next we look into a slightly more complex version, where this x, y, z, these numbers are 16-bit numbers. So, instead of being 8-bit number, they are 16-bit numbers, but 8051 will do 8-bit addition only. So, we have to be careful that from one stage to the next stage. So, the carry has to be propagated. So, what we do? So, now individual 7, 8, so individual locations are 16 bit, the number x is 16 bit. So, it is so we assume that at location 78 hex we have got the number x. So, the location 78, 78 and 79 they will hold the value of x, and then 7a and 7b they will hold the value of y, and this 7c and 7d they will correspond to the variable z, they will correspond to the variable z. So, this x, y and z we are defining their addresses as 78, 78, 7a and 7cx. Now, the program that we write is like this, that first we get the content of x into the A register. So, first byte 78 the byte the memory location 78 content comes to the A register. So, if this is the location 78 and this is the location 79. Now, since Intel follows the convention that the higher order byte will be at higher order address. So, here I have got the x, the lower part of it, and at the next location I will have the higher part of it. So, first the lower bytes are to be added. So, the 78 memory content of memory location 78 comes to A, and then add a comma y. So, this will add the content of memory location 7a with accumulator, and the whatever be the result. So, that we are storing at location 7c hex, and then content of memory location x plus 1, that is x is 78. So, 78 plus 1 79. So, the content of memory location 79 will come to A, and then we will be adding the content of memory location y plus 1, that is 7b with that A, and here instead of using add we are using add c, because previously some carry would have been generated and that carry has to be added now, because so we have got 16 bit numbers. So, two 16 bit numbers. So, we just added this lower order byte. Now, from here there may be one carry generated. So, that carry has to be added in the next phase. So, that is why this ADC is used. So, this ADC instruction. So, this will be adding A and y plus 1, and the carry will also be added, and the result will be stored at memory location z plus 1, that is the location 7d, that is higher order byte. So, it will go to the higher order address. Okay. So, next you see the subtract instruction, SUBB, subtract with borrow. So, subtract with borrow. So, this will be doing like say a comma SUBB a comma hash 0x4f. So, what it will do? So, accumulator will get a minus 4f minus c, but we do not have any sub instruction. So, there is no instruction where this b is not there. So, this we do not have any instruction where this b is absent, though we for add we have got add and add c, but here we do not have anything only. So, whenever we are doing a subtraction, so we have to be careful that we clear the carry first. So, whenever before doing any subtract operation we have to clear the carry first, and then we have to say like subtract with borrow a comma whatever subtraction we are interested in. Okay. So, that way we have to do it. Then we have got the increment and decrement instructions like INC A, it increments A, then INC byte, it increments byte, INC DPTR, it increments the data pointer. Similarly, we have got decrement A, decrement byte type of instruction. The increment and decrement instructions, they do not affect the carry flag. So, this is one difference compared to say 8085, where they were affecting the carry flag, but they will affect the 0 flag, but they will not affect the carry flag. Okay. So, the only another interesting thing that we have is that we can only increment the data pointer, we cannot decrement the data pointer. So, if you have an array and in your external storage, and if you have an array in your external storage and you say that so DPTR is pointing to this, then for accessing successive locations, so you can increase the DPTR value, but if you want to go upwards, so that is not possible. So, you cannot decrement the DPTR value. So, for that purpose you have to use the DPL register. So, you have to use the DPL register. So, you can increment decrement the DPL, but whenever you are using a pair, okay, whenever using a pair, so you cannot do this thing. So, you have to write in DPTR is always increment only. So, next we will look into an example of incrementing a 16-bit word. So, so assume that the 16-bit word is stored in the pair R3 R2. So, R3 has got higher order byte, R2 has got the lower order byte. So, first we get the content of R2 into A register with add A comma hash 1. So, rather than increment, because if I could have used increment here, but if I use increment instruction, then the carry flag will not get affected. But since it is a 16-bit addition, we want that the carry should be generated. So, when this addition is done, so when you are adding these two, this carry should be generated, so that this carry can be propagated to the next stage of addition. So, that is why instead of doing this the increment, we use this add 1. Then the result we are storing in the R2 register, and the R2 register value is incremented, and then we have to, so it may generate some carry. Okay. So, we so then R3 value is moved on to this A register, then add C A comma hash 0. So, this will be A, we already have R3, and if some carry has been generated, so that carry will get added, and since R2 is already added, so we do not have this R2 to be added again. So, this is 0. So, that way we get this ultimately this A value has to be moved to R3. So, this R2 R3 pair is incremented, and R2 is incremented by 1. If a carry has been generated, that carry gets added with the content of R3. That is how this program is executing. So, this way if you are doing 16-bit operation, so many a times instead of using the increment decrement instruction, we have to use this add instruction or subtract instruction to make the program correct.